Assalamualaikum and hello everyone. We'll meet again in EMV521 Wastewater Management MOOC series. Today we will explore physicochemical wastewater treatment methods. These processes rely on physical forces and chemical reactions to remove contaminants, especially suspended solids, colloids, dissolved pollutants, nutrients, and some organics. This chapter will extend your understanding on how these methods work, where they are used, and their strengths and limitations. These are the learning outcomes for today's lecture. At the end of this lecture, students should be able to, the first one, explain physicochemical wastewater treatment options and mechanisms. And secondly, discuss the advantage and disadvantages for selected physicochemical wastewater treatment. Physicochemical treatment combines physical separation processes with chemical reactions to increase removal efficiency. These processes are commonly used as pre-treatment, primary treatment, or intermediate treatment before biological systems. They improve wastewater quality by removing solids, neutralizing charges, and eliminating contaminants that biological processes alone may not handle effectively. Screening is the very first step. It removes large solids such as paper, plastics, rags, and debris. Grit removal targets sand, gravel, and other heavy particles that can damage pumps or reduce treatment plant efficiency. Advantages include low cost and simple operation. They protect downstream treatment units. However, screening and grit removal do not significantly reduce pollution. They only remove physical debris. Sedimentation uses gravity to settle suspended solids. It is commonly applied in primary clarifiers to remove settleable organic matter, reducing the load on secondary biological processes. It is effective for heavier particles, but not very effective for colloids or very fine particles, which tend to remain in suspension. Sedimentation tanks also require relatively large land areas. This is one of the most important physicochemical processes. Coagulation neutralizes the electrical charges that keep colloidal particles stable in water. Chemicals known as coagulants, such as alum, ferric chloride, or polyaluminum chloride, destabilize these particles. Flocculation then uses gentle mixing to bring particles together to form larger, heavier flocks that settle easily. This method is excellent for removing color, turbidity, fine solids, and even metals. Its major limitation is the cost of chemicals and the large volume of sludge that needs to be handled and disposed of. Chemical precipitation transforms dissolved contaminants into insoluble solids that can be removed. Common applications include phosphorus removal and heavy metals removal. For example, addition of alum or ferric salts can precipitate phosphate, and lime can precipitate certain metal hydroxides. This process is highly effective for specific dissolved pollutants. Adsorption involves attaching contaminants to the surface of activated carbon. There are two forms: powdered activated carbon (PAC) and granular activated carbon (GAC). Activated carbon is extremely effective at removing dissolved organic compounds, micropollutants such as pesticides or pharmaceuticals, taste and odor causing compounds, and residual chlorine. Its main drawback is cost. Carbon must eventually be replaced or regenerated. Ion exchange is useful for removing dissolved ions by exchanging them with ions attached to a resin material. This method is excellent for targeted removal of hardness ions, ammonia, nitrate, and certain metals. The advantage is highly specificity and the ability to regenerate the resins. The disadvantage is managing the regeneration solution, which contains concentrated waste brine and the overall high operational cost. Air stripping removes volatile contaminants by transferring them from the water phase to the air phase. It is commonly used for volatile organic compounds, VOCs, and ammonia. This process is simple and cost effective, but it transfers pollutants to the air. So additional air pollution control, such as activated carbon filters, may be required at the exhaust. Membrane treatment involves filtering water through a semi-permeable membrane. Different membranes have different pore size. For example, there are microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Membrane system can achieve very high effluent quality and are used in industries, recycling systems, and advanced water treatment. Major disadvantages include membrane fouling, high energy cost, and relatively expensive maintenance. To summarize, physicochemical treatments complement biological systems by targeting solids, colloids, metals, nutrients, and certain organics. The right method depends on wastewater characteristics and operational needs. When selecting a treatment method, engineers must balance effectiveness, cost, sludge generation, and complexity. Each process has trade-offs, but collectively, they form the foundation of effective wastewater management. That's all for this topic. My name is Razi Ikhwan, and until we meet again, goodbye. Assalamu alaikum warahmatullahi wabarakatuh.